Hi everyone, I'm Will, and I'm going to talk a bit about methods for inferring the end of infectious disease outbreaks. So it has been pointed out to me that that title is a bit vague, so I'll go on to explain exactly what I mean by that. But just as a way of a quick introduction, I'm a postdoc in Oxford working with Robin Thompson, and some of my research interests include modelling the start, and as I'm going to describe here, the end of infectious disease epidemics, as well as models for linking within host and population scale epidemic dynamics, as well as more recently the impact of climate change and climate variability on infectious disease outbreak risks. So please do come and chat this week if you're interested in talking about any of those things. Cool, so on to today's talk. So my main case study of interest here is Ebola virus disease. So we're going to talk about fairly generalizable methods, with Ebola being the main case study we're going to talk about. So I'm guessing everyone here knows a fair bit about Ebola anyway, but just to reiterate, Ebola is a really severe disease. So estimates of the case fatality rate vary quite a lot between different outbreaks, but they're in some range of 25 to 90%. So even the lower estimates are very high. And because of this, Ebola outbreaks are met with really stringent interventions, with some of these being surveillance, case isolation, contact tracing, safe and dignified burials. So there's been a lot of problems in previous Ebola outbreaks with transmission happening after death from patients during burials, as well as more recently vaccination and then risk communication as well. So obviously these interventions are very restrictive as well as being very expensive. So we want to have them in place as long as necessary, but equally we want to remove them once it's safe to do so. So the key question we're thinking of is, following the final case in an Ebola epidemic or an outbreak of a similarly severe disease, when is it safe to remove these interventions? So there is some existing guidance from the World Health Organization that says for Ebola, we can declare the outbreak over 42 days following the outcome of the final case. So where this figure comes from is that the maximal incubation period for Ebola is believed to be about 3 weeks, 21 days. So if we wait the maximal incubation period after the final case, and then wait that again just to be safe, then we should be fairly sure that the outbreak's over. But then more recently, a number of studies have suggested using mathematical methods to infer the end of outbreak probability. So this is the probability that a specified time following the final case, there are no future cases that are going to appear, as an alternative method to determine when to declare the outbreak over. So now I'm going to describe a few different methods, all based on a branching process model for estimating the end of outbreak probability. And these methods all have sort of a common set of inputs. The first being the disease incidence data, the second being the offspring distribution. So this is the distribution of the number of transmissions from different infected individuals. And for Ebola, this distribution is known to be very overdispersed. In other words, there's a high degree of superspreading where a lot of infected individuals don't transmit the virus at all, but a few individuals cause a large number of transmissions. And then we have the serial interval, so the distribution of intervals between symptom onset dates in infector-infectee pairs. And then for some of the models, we're also going to use the outbreak transmission tree. So in principle, via sort of very intense contact tracing that occurs during Ebola outbreaks, we might be able to reconstruct this transmission tree, at least for smaller outbreaks, but in practice, and especially for larger outbreaks, this might be unavailable. And then between these inputs, we're then able to use our method to estimate the end of outbreak probability at different times during the outbreak. So I'm going to talk a bit about three different methods. So first of all, there's what I'm calling the Nishura method, which is an existing approximate analytic approach. So here by approximate and then exact, I mean this is sort of under the assumed transmission model, that even under the branching process model we're using, this existing method that's sort of the most common in the literature only approximates the end of outbreak probability, particularly when transmission is very overdispersed. And so this method doesn't require the transmission tree, it's just the three main inputs I discussed. And then in 2 recent papers, we've developed 2 different novel methods for inferring the end of outbreak probability. So first of all, we developed a novel exact analytic approach for deriving the exact end of outbreak probability whenever the transmission tree is available. And then in a later paper, we combined this earlier approach with data augmentation MCMC in order to infer the exact end of outbreak probability when the transmission tree is unavailable. So now some results. So we started just looking at simulated outbreak data, and then at each day of the outbreak, based on sort of the case data so far, we estimated the end of outbreak probability with the different methods. So then the main thing to note is that the MCMC and trace method gave pretty comparable end of outbreak probability estimates for both of these simulated outbreaks, and this was indeed true over a load of different simulations we considered. And this blue shaded region here shows sort of the range of different end of outbreak probability estimates in different MCMC iterations. And it's essentially saying we don't know the transmission tree, but if we did conduct more contact tracing and obtain the transmission tree, this is the range of end of outbreak probabilities we can expect to obtain. So our 2 novel methods gave fairly similar results, sort of regardless of whether we know the transmission tree or not. And I guess it's good that the black dotted line, so the true transmission tree, lies within this blue shaded region, whereas the existing approximation underestimated the end of outbreak probability following the final case. And again, this was fairly consistent over a range of simulated outbreaks. So then we went on to consider some real-world Ebola outbreak data. So we considered 2 outbreaks, both in the DRC. The first one was a very small outbreak, only 8 cases, and the advantage of considering this data set was that we did know the transmission tree exactly, so then we were able to compare these 2 methods. And what we saw was that the MCMC method gave very similar end of outbreak probability estimates again, compared to the trace transmission method. And then we considered this larger outbreak in the Equateur province of DRC, and because we only had disease incidence data here, we were just able to apply the MCMC method and estimate the end of outbreak probability following the final case. So I guess a big thing to notice for both of these models is that this red dotted line here, which represents the actual date on which the outbreaks were declared over, for both the 2 outbreaks, we got very high end of outbreak probability estimates by this time, which suggests that at least in principle, it might have been safe to declare these outbreaks over before the actual time of declaration. So then we looked at this a bit further and thought about how we could use these end of outbreak probability estimates as an alternative basis for determining the time of an end of outbreak declaration. So we considered taking a threshold risk of future cases occurring. So this is a choice for the policymaker depending on sort of risk aversion, that say we could choose to declare the outbreak over when there's only a 1% risk of future cases. So when the end of outbreak probability is 99%. And so obviously the time at which we can actually declare the outbreak over is dependent on the threshold we're going to set. But even for fairly risk-averse thresholds, the model suggests, or both models suggest, that we could declare these outbreaks over earlier than the actual date of declaration. And then finally, these sort of shaded intervals again represent uncertainty in when we can declare the outbreaks over, depending on the exact transmission tree. And these intervals were all fairly narrow, which suggests that for this Equateur outbreak, actually conducting further contact tracing to determine the exact transmission tree may not be particularly beneficial, at least for deciding when to determine the outbreak over. So obviously I'm not saying that we shouldn't conduct contact tracing, just that precise transmission tree reconstruction may not be very beneficial for this specific question. So very quickly, I just want to mention an alternative approach that we developed in another paper. So this was using a renewal equation-based approach to estimate the end of outbreak probability. And these two approaches, so the renewal equation approach in this paper and the MCMC approach we discussed here, have different relative advantages, with the big advantage of the renewal equation approach being that it's straightforward to combine with RT inference, and that it's slightly simpler to include underreporting in that approach. Whereas the MCMC approach has the big advantage that, as I say, the Ebola offspring distribution is known to be relatively over-dispersed, and this approach allows us to consider an arbitrary offspring distribution. And so I will just briefly say that we are working in sort of ongoing work to come up with an approach that does combine the sort of different relative advantages of these methods. Cool, so I'll just end on a quick summary that these mathematical methods to estimate the end of outbreak probability can be used to inform when interventions can be removed safely for severe disease outbreaks. And secondly, it may not be necessary to collect comprehensive contact tracing data to resolve uncertainty into when to declare an outbreak over. Cool, I'll leave it there.
Thank you. We've got time for one or two questions. There's one here, and then next was back there. Yes?
Thank you for the nice presentation. So I have two questions. The first one is when you're talking about the offspring distribution, presumably it's changing with the intervention. So, like, which offspring distribution do you consider? And the second one is about the impact of underreporting on your estimates of the.
Yeah, so with the offspring distribution, here we just had a fixed offspring distribution, so not accounting for interventions. So in principle, you could adapt this to have a changing offspring distribution over time. I think it probably wouldn't make a big difference because only sort of the more recent cases are really contributing to the end of outbreak probability sort of after the final case. So then the offspring distribution we use was sort of reflecting a fairly low value of the reproduction number. But yeah, in principle, you could extend it. With underreporting, I guess, of course, the more underreporting there is, the longer you'd have to wait to be confident in making an end of outbreak declaration. And so here, the aim was to develop these methods in sort of the first case where we do have good reporting, which seemed to be the case, at least for the smaller outbreak. But yeah, definitely it is a big limitation of the method so far, and it's something we're working on. That actually the renewal equation approach, we did consider underreporting a bit, and yeah, we're working on it further.
Good. I think Paul.
I was just wondering why they declared the outbreaks over a longer time after the recommended WHO period than.
So the actual time of declaration is based on the outcome of the final case. So when the final case, I think in these two outbreaks recovered rather than when it was reported. So then you have that gap first.
Okay, thank you. There were other hands up, but if you can take it to Slack to continue discussions, Will, thank you very much.
Cool, thank you.